hangout of this course, Gravity. So welcome to all the Gravity learners, but also welcome to people outside, since we have opened this hangout to everyone. You know that this hangout has been rescheduled, and for the reason that the tragic events in Paris. But as I said this morning in a message to all the learners, we thought it was important to keep going, to keep having the same activities, the activities plan, and to show that indeed nothing can stop us. And for the reason that the tragic events in Paris, but as I said this morning by message for the learners. So let me just do a few technical changes, because we are hearing my voice with some delay. If you experience any technical problems, then you should let us know on for example, on either on the platform or on Twitter or on Google+. Okay, so let us start the questions. And so we have a chance of having George here, so let me ask a few questions that you have asked. So I remind you that you have asked questions on the different media. We picked up some. Of course, we are not going to answer all of them. We'll try maybe on the platform on Futurelearn. We'll try to answer a few more, by writing, but we'll try to pick up some questions that come again and again. And of course, you can ask your question online, and then we'll try to answer. Volker and Maria are next to me, and they are going to send, pick up some of your questions, and we might answer them online. Okay, George, let me start with a question by Carol. I've just mentioned the first name because my pronunciation might not be very good for your last names. Well, Carol wanted you to explain again what was your discovery, the discovery that awarded you the Nobel Prize. We already discussed that, but it might be good that you start with this.
So the Nobel quote was about discovering the black-body form and the anisotropy of the cosmic microwave background. That's pretty dry. What they're really quoting is that through experiments we did beforehand, but particularly on the Cosmic Background Explorer satellite, COBE for short, we showed that this radiation was radiation that came from the Big Bang. And we showed that by showing it had such a precise form, that of what we call a black body form, but it's the form you can get only when something is in precise equilibrium, and that you could only get, as far as we can see, by having the early universe be very hot and very dense and many interactions, getting to equilibrium the same way radiation goes on in the sun and so forth. The sun has very close to a black body, but not as good a black body as the universe. So the first part was establishing that this was radiation coming from the birth of the universe, like the creation of the universe. And then the second part, which is what got more attention, was that we used that light to make an image of the embryo universe, so that we could see what the universe looked like when it was quite young. And that allowed us to do a lot of other things, which we'll talk about presumably a little later on. But measure the geometry of the universe, find out what the constituents were of the universe were at that time, and find the tiny variations that are later on going to grow to become the structure we see, the stars and the galaxies and the clusters of galaxies. So it's the quote is shorthand for saying we really established it was the radiation from the Big Bang, and we really established that we could measure things about the universe early on. And because of that, the whole industry of research developed for looking at this radiation and trying to understand the early universe very precisely.
Okay, we have a question from Marcel, who is asking you whether the temperature fluctuations, so those fluctuations from the CMB, the cosmic microwave background, how do we know they are the sort of fundamental cause and they are not caused by the noise generated from the galaxies, which are between CMB and us?
So that's an interesting question, and now the question that we had to deal with at the time of discovery, which is only 25 years ago, which was, how do we know this is really coming from the universe as a whole and not from the galaxies that are between us and the beginning of the universe? And there are several ways to do that, but the most important one was that we use the fact that when we measure light coming from galaxies, or light waves coming from galaxies, we find that they have a very, strong temperature dependence, frequency dependence, if we compare it to the black body radiation coming from the universe. So there is energetic electron spiraling magnetic fields in the galaxy, and they make radiation, which we call synchrotron radiation. It falls very quickly with increasing frequency, whereas the black body radiation is flat across that range. And then there's radiation that comes from dust, and that's rising very quickly, but at higher frequencies. There's a gap in which the universe dominates. And so that's what we did the early time. And the succeeding satellites, WMAP and Planck, where we had more wavelengths, more frequencies, which we observed, and more angular resolution, because we had bigger antennas, dishes that allowed us to make them. There we're able to show even more definitively that the frequency dependence is the dependence of the radiation, but we're measuring more precisely, so we're trying to get it more accurately. But we can also see on the various angular scales. On COBE, we just had about a 7-degree resolution. Now we're down to much less than half a degree, quarter degree, tenth of a degree. And galaxies themselves are quite small. Compared to that, they're usually 1/60th of a degree, whereas the fluctuations we see in the microwave background typically are 1 degree and bigger. And so we can distinguish them both by the frequency dependence and by the angular dependence. And so we're extremely confident this is not radiation. These fluctuations we're seeing is not dominated by signals from galaxies or even clusters of galaxies, but is dominated by the universe as a whole. And it's only the small effects that we're worried about. Those galaxy calls them or not. So we're quite confident that we understand that quite well, but we have tremendous resolving power. And the fact that on the Planck satellite, we have 9 different wavelengths that we make measurements. Plus we have very good angular resolution. So that, I think, is a problem we're confident about.
Okay, we're talking about discovery, but you make discoveries with instruments. So we have a question from Rowena, who is asking you to give a little more details about the instrument which is used on the COBE satellite that allowed the discovery.
Okay, so a large part of my research life has been developing the instrumentation, the techniques, and the various things that we do in order to make these measurements. And what we ended up doing is, at the beginning, making something that looks like a radio receiver. It has the same basic concepts. It takes the radiation that comes, microwave radiation that comes from the sky, and runs it through a receiver, very much like a radio receiver. Back in the days when people had broadcast radio, most people do the internet now, and broadcast television, those kind of receivers. But we made some that are very careful, so they had very low noise and wide bandwidth, so we can look to see the signal coming in from the sky. And then we had more things that we had to do, which was we had to actually design antennas that we could tell the radiation is coming from the sky and not from the air around us or the earth or the things behind us, because the earth temperature is about 300 degrees above absolute zero, 300 Kelvin, which is 20 degrees C which is roughly room temperature, is about 300 Kelvin above absolute zero. And whereas we're looking at the microwave background being 3 degrees above absolute zero, 3 Kelvin, and we're looking for fluctuations at the beginning, which were on the scales of 30 microkelvin, 30 millionths of Kelvin. So we had to be very precise in knowing that we're taking only radiation from the sky, which is, we're looking for 30 microkelvin variations compared to 300 Kelvin. Right? So it's more than a factor of 1 million difference. So we had to be very careful to do that. And then what's happened over time is we've been improving the sensitivity of the receivers, both the radio receivers and things we call bolometers or incoherent detectors that just measure the total power. We've been improving them with a sensitivity improvement, which is roughly doubling every couple of years. So it's like Moore's law, but it's sensitivity of the instrument. And so when we moved from Kobe to Planck, we had a big improvement in sensitivity. I mean, Kobe to WMAP and the Planck, each time was a big improvement in sensitivity. We now have ground-based observations and everything where the sensitivity is much better and the number of detectors is much increased. So with Kobe, we had a few detectors. With Planck, we're up to approaching 100. Now the ground-based detectors are in thousands, and we'll go to tens of thousands. So the instrumentation has been improving very significantly, very systematically over time. But it's basically starting with same simple idea as what radio receivers were like 30 years ago, and improving upon that and making them better and better.
Okay, so that was what the path with discovery. Now there's a question about the future from Winston. What other information would you like to get out of a CMB?
Okay, so one of the reasons we kept putting so much effort into improving both the angular resolution, so we can see things on finer and finer scale, and the sensitivity, is the more precisely we measure the sky and measure these fluctuations, the more we're able to tell about the universe. So we're able first to measure the geometry, that is the curvature of space, but then we're also see sound waves and other features that we see in the early universe, and those tell us what kind of fluid the early universe is made out of, what fluid is made out, what constituents are in the fluid, how much dark matter, how much dark energy, how much ordinary matter, how much neutrinos, and so forth. Those are things that we can determine. And we can also test to see if our ideas of gravity, that is Newtonian gravity and relativity, hold true over large scale. And so we have done a very good job of making these improvements and going far in this. And we still think that there's more to learn. We have many colleagues who are putting together proposals to measure the sky polarization of the radiation more and more precisely, because it gives you more information and you can measure these cosmological parameters more precisely. But it also allows you to test whether the laws of physics as we know them continue to be valid over those distances. And we also are hoping to look for the definitive signs of inflation, that is, seeing the telltale signatures of the fluctuations, the gravity waves produced in the early universe that would be produced during inflation. That would tell us the energy scale of inflation and that we have everything on the right track. That's one of the big breakthroughs that we don't know how to predict, but there's a lot of other stuff we can actually predict how much better we would do if we can make those measurements. But I think we're reaching a peak in the sense that we've discovered a lot of what we're going to discover. What we're now doing is refining our measurements and refining our understanding and testing that our models are right. But it's still a very exciting time, and it's still something very worth doing.
Okay, so let's take a question online. Those where we had picked up in the question which were asked before. And I think there's one for you, George. You're very good at answering this type of question. Which asked, this is from Ellen. No, I'm sorry, Helen, rather than H. Which aspects of cosmology have the largest impact on our lives?
Okay.
I'm listening.
Yes, you gave that to me on purpose.
Yes, absolutely.
Okay, so there's a lot of different things you could answer to that. But let me say there's two aspects of why people pursue things like cosmology. One of which has to do with kind of a cultural aspect, and the other has to do with a scientific understanding of things. And the thing that has had the biggest impact on society today is the cultural impact. So for every group, every tribe, every culture has always had a story. We call it a creation myth or a creation story about how the world came into being and what's the relationship of a particular people, a tribe or culture to the rest of the world, and why they're special or what their job is and what they're doing. And now we have a story which we have strong evidence for, we can back up, we can refine, so forth. But it's a story which is, for all of humanity, a story about how the universe came into being and a story, we think about how eventually the solar system came into being, and eventually how life came to arise on the Earth, perhaps in many other planets in our galaxy or in neighboring galaxies. And so it's a tremendous background information about our culture. It gives everybody a sort of a common starting point to think about, who they are, what's life like on the Earth and so forth. And this is particularly relevant as the human civilization, human race has got to the point where it's become global in the sense that not only are humans everywhere on the Earth, but they're having a big impact on everything on the Earth. And so it's becoming more unified by a number of different reasons. And instead of being separate people have to start thinking about what's common, how they're going to manage the Earth. So that's what the biggest impact is today. There will be secondary impacts on the spin-off science and on perhaps other things we'll learn. But the big impact is the cultural impact.
Yeah, let me add something. This is not strictly speaking cosmology, but that has to do with explosions in the universe. We've well seen the last week that black holes are coming from such explosions, and it is in the explosions of stars that the heavy elements of which we are made are formed. So in a sense, that's what some people say, that we are stardust, in the sense that the heavy elements, carbon, iron, and so on, are made within stars, which then at the end of their life are exploding. And so that has a direct effect on us, because in a way we are part of this filiation coming from the star explosions. And moreover, these star explosions are also leading to some cosmic rays and things like that. And probably also we have been an evolving species because we receive this cosmic radiation. And so that has also some impact. Radiation can be bad for your health, but probably that also leads to evolutions to, we are mutants in a sense, because we have been evolving. And so I would say that that's also, understanding all this and the role of all this is also quite important. Okay, let me ask one question that you have been many to ask. That has to do with the flat universe. So I'll try to answer it in written form, but you have been asking, many of you have been asking about this notion of flat universe. Okay, so let me come back to what we physicists mean by flat. And I think the reason you have difficulties in understanding this notion of flatness is so someone
You said the secret word.
Yeah, okay, so I must have said something wrong because the phone has been ringing. So let me come back to what I was thinking. Yeah, this notion of flatness. We use the word flat in a different way, with physicists than in sort of everyday language. For example, if you take this table here, you would say it's flat. If you take the room around me, maybe I should actually tell you where we are. We are in the François Center, which is a space data center. We'll return to this when we go to the LISA Pathfinder mission. But we wanted to welcome you in a place where we are doing science. And so this is where you get data from the space and analyze the data. Probably we'll come back to that when we have the third hangout. Okay, so let me return to this room here. You might say, okay, this is not flat. We physicists would call it flat. So, I would like to stress that what we call flat is something different from the everyday sense. We don't mean planar. We don't mean two-dimensional. Two-dimensional, that means that this table, the surface of this table, has two dimensions. I can, say this point here is at a certain distance from this edge and another distance from the other edge. It has got two dimensions. This room here has three dimensions. I need three numbers to tell you, where is the point in this room. Now, we still say, we physicists still say that this room is flat in the sense that the laws of geometry are the ones that you know. the ones which were taught to us by Euclid and by the Greek mathematicians. So for example, if you have two parallel lines in a flat universe, when they all stay parallel, they will never meet. If you take the sum of the angles of a triangle, then it will get to 180 degrees. So that's what we call a flat space, and it could have 2 dimensions like this table, it could have 3 dimensions like this room, it could have 4 dimensions, 5 dimensions, and so on, but let's say our own space has 3 dimensions. Now, I kept telling you that say space-time is curved, so why suddenly space is flat, and why did we discover this? Well, the reason is, of course, mass is curving space-time. So close to a mass, and space is not really flat, it's slightly curved. The question that one asks when we're studying the CMB, for example, is whether the universe itself is also curved, the full universe is curved, or it's flat. And it's flat in the sense of that we physicists are using. And indeed, the discovery in recent years is that most probably, we can never be sure, but most probably according to what we observe nowadays in the universe, most probably the overall space is flat, again, in the sense of what I was telling you, in the sense of Euclidean geometry, if you want. Okay, I'm sure we'll come back to this question over and over again, but I just wanted to make sure that you understand that when we say flat, we don't mean flat as this table and two-dimensional.
So let me add that if you think about light coming to us from the really distant, faraway universe, the light travels in pretty much a straight line, which is what would happen in Euclidean space, in the sort of the flat space-time. If the light happens to go near a galaxy or a cluster of galaxies, it will be slightly curved in its trajectory because space is slightly curved. But if you just take the path over a long distance, the average is pretty much a straight line. It's only when it goes very near a cluster of galaxies or a galaxy or a massive star you actually see evidence for the bending. But just because there are places where a space is bent doesn't mean that when you average over all of space, you don't get the average of zero curvature. In some places it's curved in a positive way like a sphere, in other places it's curved in a negative sense like a saddle, and the sum averaged over a long distance is zero still. It's flat.
Now that I said that we are in the space data center, there is, I think, a question which comes from Kathy, and that is really well suited to where we are. She's asking, how have computers impacted the way cosmologists do research? Why don't you give it a try?
I see. Well, that's easy. We can even turn it around and ask, how has cosmology impacted computers? Because in order to do these maps of the cosmic microwave background, we've actually been challenging the massive computers. It's not enough to go out and just scan the sky and put the data points up. We actually have to scan the sky many times, average the data together a lot, because we're dominated by the noise of the receiver and from other kinds of things, and the drift that might be in the receiver. We have to do a lot of data averaging, scan many times. It's like if you ever do a Skype call or a video call, you're lucky if the reception is really good, you get a nice clean picture. If you don't, then you have to keep refilling it in, and eventually the picture gets sharp. That's exactly how it is. We have to keep scanning the sky and filling it in. But in the end, it means we solve very large problems where we're trying to generate a map like this one. This map has 10 million pixels in it, which is much more than your ordinary printer can do or a TV screen can do, because we're trying to find out so much. That's a very challenging mathematical problem, and we eventually convinced government agencies to fund very large computers and let us use very many parallel processors. So typically to make that map, we were using 4,000 processors for relatively extended time periods just to produce that map, and then to go and analyze it and interpret that in terms of what cosmological world we're living in took even more computer time. So the answer is we could not have done this research without computers. but in fact, we've actually pushed the computer makers to make more powerful computers and to build more powerful systems so we could do this problem.
Actually, since this week we're studying the dark energy, the experiments which are trying to observe the universe and to try to detect the properties of dark energy are using very large surveys of galaxies and very deep surveys of galaxies. So they look for very distant galaxies. And so they need lots of pixels in order to be very precise, even for very faint sources. And so they use a huge amount of data. If you look at, for example, at the end of this week, what is being said about the space mission Euclid and the ground telescope LSST, you'll see that the amount of data is enormous. And exactly as you said, I think if you look at this about LSST, you'll find out that Google is itself interested in this type of data because this is posing some very challenging problems, and so they want to know, what those challenging problems that physicists have to face in this field. So we are getting into an age where computers, and not just computers, but searching for data, what we call data mining, is extremely important. And as a matter of fact, this is why we have been creating this center here in Paris. It's precisely to do this.
And I can add, I mean, the missions are enough expensive and involve enough people that we don't just sort of build it and do it and try and fix it later. We spend a huge time and effort to do simulations to see what the sky would look like, to see what our data would look like, to see if we can reconstruct it before we ever actually start making the hardware, because we do that. So it's a collaboration between theorists and data analysis and experimentalists, instrumentation people, to actually design the experiment and see that we'll get the science out of what we expect before we ever actually start spending the huge amounts of money to build a satellite.
Okay, let us come back to CMB and your discovery. I realize there is another question from Manuel, who asked, how did you come up with the idea to go and look for fluctuations with CMB? Did you assume that you were going to find, or did you just stumble upon the discovery by accident?
Okay, so that's an interesting question, because in the end we didn't make the discovery by accident. We kind of understood what we were going to see, but it was not, when we started, it wasn't so clear. And when I started very many years ago with ground-based and then airplane and balloon-borne, we were looking for relatively simple things. We were looking to see the motion of our solar system and our galaxy relative to the other matter in the universe. That was the first discovery. The next thing we were looking to see was, is the universe rotating or not rotating? And we didn't find it to be rotating, but then we started discovering there were other features and other things. And as the theory and understanding developed, as we made more and more measurements, we came to understand that it was very important that there be these fluctuations in order to explain where galaxies came from and where clusters of galaxies. There's very much structure on many scales. We needed to see fluctuations on many scale, and then for something that I was worried was going to be a background, because there were galaxies, so there must be fluctuations with galaxies. It became something where there was really relevant science, because as we understood, we needed things like inflation and we needed a whole spectrum of fluctuations. Then there became a lot of science and a lot of things we can do. It's what we call spectroscopy, when you see many different lines. So when people were studying stars in the sun, they started seeing lines. That means they could start determining what elements there were, what the sun, what other stars were made out of, and so forth. The same thing is true of the universe. Once we started understanding that, then we knew we needed to look for these fluctuations. And we even had some theoretical papers predicting what the minimum level should be. And fortunately, we found them, and now we know we're on the right track, and so forth. But until you make the measurements, you don't know if that theory is going to be correct or not. Could be we'd be forced into something new. Fortunately, we discovered it, and then everything fit together, and then we followed up with more missions and more studies. So it's a huge field right now.
And looking into the future, there is a question from Javier, who is asking that now that Planck is making polarization maps, what kind of information is it given, would be given by these maps? And I guess that's the same story, but now with polarization.
Okay, so one of the things Planck has published first its half of its data in 2013, the second half this year in 2015. Next year, it should publish both polarization maps and a more improved, more calibrated and slightly corrected versions of the data. The polarization maps are more difficult to make because they involve orientation and two components as opposed to just one spot in the sky. And there are more possible errors, so it's taking longer to analyze that data. But the signal level is also smaller. We know if we see fluctuations in the sky, then the fact when they scatter off of electrons the same way when light scatters off the surface, off the screen, when it becomes slightly polarized, it should be slightly polarized. We can predict what that pattern looks like, and we can see what signals we can see. And we also pick up some additional information, and that additional information gives us more information on what the universe is made out of, what's going on. But it also gives us extra things. We know the universe, when it was 1,000 times smaller, was when it started to become neutral. And it stayed neutral for a long time, but about when it was between 10 and 6 times smaller, it began to be reionized, and that is the little bit of hydrogen that hadn't dropped into galaxies and stars was ionized by the very hot bright stars, and that made some free electrons, and that will scatter some of this light again and produce an extra polarization. So we should be able to test when the universe is reionized in a different way, and we already have limits on that. One of the things we'll learn about. But another thing, as I mentioned, we're looking for this particular pattern that would come from inflation. And there was a report earlier this year that a ground-based experiment for the South Pole had discovered this, but then Planck showed from its map and polarization of dust that it probably was mostly dust what they were seeing. But they're going to go out with new results. But it taught us that we had to be more careful, and it taught us that we needed more frequencies to separate various things. But we can expect we'll get more limits on how much signal could be coming from inflation, and that'll tell us something about the energy scale. It may not tell us exactly what it is, but it may push it down to a level where we have to have different, it rules out some possible models of inflation and puts us on the track for what we think might be right. So it's mostly improved measurements and improved understanding and cross-check that we understand things. But getting things more precise is very good. But there's a chance we'll learn some new things about the reionization of the universe, and particularly about inflation, which we think is happening at least 10 to the minus 30 seconds or earlier. So it's an exciting potential. We'll have to see what happens.
Okay, so let's pick up some questions about infinities and infinite. You have been many to ask questions about that. So let me first pick up a question by Matthew. We say, is it that when we say something is infinite, it's primarily because we can't comprehend it? Do things associated with the concept of infinity just signify the limits of our comprehension? I would answer that there are two different things. First, when we say a quantity, a physical quantity becomes infinite, like for example at the Big Bang, temperature of the universe or the density of the universe becomes infinite, clearly that means that this is a limit of our theory. So whether again it's we have to just change our theory, or do we have to on the other hand this is the fundamental limit of the theory? That's a further question. But we know that temperature is not infinite, or we know that an energy density cannot be infinite. And so, as I said, physicists at this point are searching for new theories where, for example, the density of the universe would not be infinite. So that's one thing. It's different when we say the space-time is infinite, or if you want, the universe is infinite. We had many questions about that. You seem to have problems with that. If we come back to a flat space-time or flat space, and if you have two parallel lines that never meet, then flat space has to be infinite. So if indeed our universe is flat, it has to be infinite. Now, of course, in the back of your mind, you have the idea that it cannot be infinite, and I think that's a question which was posed by Gareth, was saying, if the universe is infinite, how can it expand? And again, this is the same idea. If it's infinite, just remember the example that I took of the rope, which is infinite and which is expanding or contracting. There's nothing wrong with that. It might be difficult to imagine, but to me, and that's probably personal, it's even more difficult to imagine a finite universe because you come to an edge and what's on the other side of the edge. So the universe indeed could be infinite. Now, I was going to say that you might have difficulties viewing this because you have in the back of your mind the fact that the universe started when at the Big Bang in a very tiny region. That's a false image. The universe could be infinite at the Big Bang. There could be Big Bang everywhere in the universe. So that means that every tiny region would explode into a very large region. That would be an infinite universe undergoing a Big Bang. I don't know, George, if you want to add something to that, but that's...
Yeah, well, actually, I have found when I'm teaching students, usually they don't have a trouble with an infinite space because they're used to printing presses or manufacturing, and you can imagine an infinite number of cans of soup or an infinite number of newspapers or something. And, the example, it's easier to imagine the universe that's infinite and flat and you just keep stretching it and it gets bigger. But it was, infinity just gets twice as big, it's still infinite and so forth. You can avoid making an edge by making the universe spherical or something if it was finite, but it'd be very big. Our measurements show us that the universe is extremely flat, and it's at least 100 times whatever curvature it has. The radius is at least 100 times what we can see in our visible universe, the part that we can see. So that whole idea of being infinite is, we don't know if it's truly infinite or if it's really just much bigger than what we can see. Either one of them is practically the same, except philosophically it may make a difference to us. The thing that I usually find students have trouble with is having a finite beginning of time. They always want to know what would happen before time began. Right? They can't imagine that time just began. There was nothing before time began. So the thing that we say, we can imagine pretty easily a universe that's infinite in its spatial dimensions and finite in its time dimension. We can also imagine a universe that's very big in its spatial dimensions, but still finite and no edges, and one that's also finite in time, and we'll see what's going on. And with this dark energy, that's possible. That's an example where the universe just keeps growing so much faster that it's effectively infinite as far as we're concerned. So there's a lot of subtleties in this, and it's something that's kind of difficult. And I can remember as a student when I was amazed to learn about infinity. And first they taught us about countable infinity. So they say 1, 2, 3, 4, and you keep counting up to infinity, right? And they said, all right, now if you consider all irrational numbers, that is numbers that are integers over other integers, like n over m, right? How many are there? And it was only that's a countable number too. And here's the math you can do that math. You can label them 1, 2, 3, 4, and even though you think you get infinity. But if you take the irrational numbers, that's an infinite number of countable numbers. So it's a higher level of infinity. And when you start studying infinities, you realize you can get into trouble in a hurry. And so, but it's very convenient for us to think of the universe as being extremely big or effectively infinite as far as the spatial dimension is concerned. For practical calculation reasons, they come out about the same. You can have the choice of what you want, right?
Okay, now that we are dealing with fundamental questions, let me pick up one from Julio. Don't quantum fluctuations violate the law of conservation of energy? I really like that question. Because we are, this is quantum physics. And I would like to stress that there is a very deep connection between energy and time. And I think probably that tells us something about the universe. We still don't know because we don't have a quantum theory of the universe, but probably that tells us something. And so, that connection between time and energy is such that you could have violation of energy. So that means that energy is not very precisely defined if you wait for for a microscopic duration of time. And so, violation of energy, or if you want, imprecision in the value of energy is allowed if it lasts a very short time. And so you see that establishes a very deep connection between time and energy at the microscopic level, and the quantum fluctuations were born at a microscopic level. Probably it tells us something if you try to apply the quantum theory, and we'll be dealing with that question, well, we're already dealing in the 4th week with that question, but we'll come back to that. If we want to build a quantum theory of gravity, so to marry the microscopic world with the, the world of gravity, the world of the cosmos, probably we'll have to deal with this question of connection between time and energy. Another question for you, George, from Carolina. How does gravitational lensing impact the CMB measurements?
Okay, so again, it's an interesting question. And I referred to this obliquely before when I said light coming from the beginning of the universe will pretty much travel in a straight line unless it goes very close to a massive star or galaxy or a cluster of galaxies. Most of the time, the light travels and it's very unaffected. And on the average, it has not deviated very much. However, the light from the beginning of the universe does get affected by the intervening structure. And there's particularly significantly by the very large scale structure. These very, massive clusters of galaxies, thousands, tens of thousands of galaxies have an impact. And so as our measurements have gotten more precise, we're able to think we understand what the pattern of fluctuations look like at near the Big Bang, at the surface of the last scattering, in this map. And then we look to see, are these things slightly distorted? And they are, and they're distorted on a scale which is most noticeably affected on the scale of these large clusters of galaxies, which are tens of arcs minutes, and so they're fractions of a degree. And so you can then make an assumption of what the universe is you're looking at, run the model to your best fit data, and try and extract a map of what the intervening material is. And so this year, Planck for the first time published a map of what it believes the lensing is. It typically is affected by things from the time the universe is half the size it is now. We call it redshift of 1, but that means light's been stretched by half of this, well, factor 2, depending on your viewpoint. And and that is very interesting because generally we're using quasars or bright galaxies to see the effect of the material closer to us, so we can start separating out where the various matter is and see if a large-scale structure has formed the way we think it has. But the effect is a very small effect. We see the signal on the cosmic microwave background on the scale of 30 microkelvin. We're looking at these lensing effects, and they're down at the few percent level. And so we think we're understanding the primordial signal very, very well, and then we see this pattern of the lensing that slightly broadens the kind of things we see, and we can interpret that and reconstruct. It's like passing through a dirty lens or something. We can reconstruct what the beginning looked like and what the lens looked like, and that's what we're seeing. So it's having an effect. It's not a huge effect, but we're making so precise of measurements that we can actually try and split those apart now.
Yeah, and I was just thinking while you were talking that there's a beautiful picture which was produced by the Planck collaboration, and you find it, if I remember correctly, in the section which is wrapping up week 3, and you see precisely the photons of a CMB, which are slightly, with a trajectory which is slightly distorted, precisely because of the gravitational lensing. And I remember I put that picture here because at that time, at the end of week 3, you knew about the CMB, you didn't know yet about gravitational lensing. And so that was sort of to make a transition. But just have a look at this picture because that's
it's slightly exaggerated,
yeah,
but it does show you what the kind of effect is. Right? So when you want to see when we draw those pictures, we did it to emphasize the lensing, not to emphasize how small it is.
From Sybil, something which touches on particle physics. Is it possible that there are other so far undiscovered particles?
Yes. So the answer to that is yes. There is always the chance. They get more exotic, and as we get more complete models of particle physics and particles, we get more limited. So we have what we call the standard model, and it just got completed within the last year with the discovery of the Higgs boson. All the particles that it predicts exist. There are other things to think about, but there are hints that there may be physics beyond the standard model. One of the things that's a favorite of many theorists, particularly in Europe, is supersymmetry. That is, for every particle we know in the standard model, there'll be a supersymmetry partner, which is much, much heavier, therefore not detected yet. And one of the, in some versions of this model, the very lightest of these supersymmetric particles is what makes the dark matter. And so, there's many people that believe the dark matter is a hitherto undiscovered particle, and it would be natural for it to be the lightest of these supersymmetric particles, because it would be the one that wouldn't decay and stick around. And so there are many people who are searching for such a thing to do it. There are other people who are thinking there are other kind of particles. We know we have neutrinos and everything. There could be a very heavy right-handed neutrino or a singlet. There could be other particles around. If they are, we should be able to figure out how to detect them or to understand them at some point. But we're still struggling to figure out what the dark matter is, what these various things are. But we certainly suspect that there are probably more particles to be discovered.
And I think what you stress also, and that's probably new. Now, you can try to discover new particles, both in accelerators, and of course, ultimately you want to discover them in accelerators, but also coming from the cosmos. And so there is a sort of complementarity between the searches in colliders, like searches at CERN, for example, and those coming from the cosmos. And probably, for example, you'll be sure about the nature of dark matter once you have observed them, detected them as particles coming from the cosmos, but also discovered the same particles in accelerators, in high energy colliders. From Anna, again, a question live. Why is there more matter than antimatter?
Okay. So this is one of the questions that has been vexing scientists, particularly physicists, for many years. And in fact, one of the people who worked on this was Andrei Sakharov, who is famous as the Russians' father of the hydrogen bomb. And he came after that to Reddit, and he spoke out about it, and he was under house arrest. One of the problems he worked on was, how could it be that we end up with a universe that has more matter than antimatter? Because if you look back in the very early universe, there were very close to equal amounts of matter and antimatter, and probably were equal amounts. There had to be some reaction or something that went on to make a slight imbalance, about a part in a billion imbalance, in order for the residual to be left. because the matter and the antimatter would annihilate. There has to be a slight extra residual of matter left behind, otherwise we wouldn't be here. And so many people have been working on this problem for quite some time. They have proposed many different possible ways, and it's a problem that we're still trying to resolve. Right now, when we do cosmology, we assume the answer. We assume that, in fact, there was equal amounts of matter and antimatter at the beginning of the universe, and then there comes a transition early in the universe in which roughly 1 part in a billion excess of matter developed, and everything else annihilated away and added to the radiation, which eventually became the cosmic background radiation.
Okay, now, yeah, there's a similar question from Chaitanya saying, does the CMB offer any clue to why there is more matter and antimatter in the universe?
Right. Well, the first and most important clue is if we look, we believe in the early universe, when it was very energetic and very hot, every degree of freedom that could be excited was excited sort of equally, because that's the best way. Random scatterings will partition everything. And that means there were equal amount of electrons and anti-electrons and photons, and photons are its own antiparticle, and quarks and anti-quarks and so forth. And in the end, we now end up with almost 10 billion times as many photons as we have of other particles. And so that's a hint that in the early days, there was roughly 1 billion times more of each of the other particles. And when they annihilated, they turned eventually into photons, and that's the residual. So that gives us this number that lets us know what the ratio is and what fraction we have to save. Now we have to go and do experiments, and one of Zakharov set down these 4 conditions. One of them calls for violation of some principles, that is, right-handedness and left-handedness being the same, and particle-antiparticle being the same. The product of those two has to be broken at some level, from around 10 to the minus 9, 10 to the minus 10 level. In order for this to happen, we have to have people who have tried to understand the universe in different ways, but we don't have the experimental determination of what the answer is.
Okay, we still have 8 minutes to go, so maybe some more general questions. We had one from, where is it? Well, from Bill, was asking, what are you working on at the moment?
Okay, so is that for me or is that for you?
You start. You start.
Are you going to talk about yours or what?
Yeah.
Okay. So I'm working on several different projects. I'm still doing some things on the cosmic background radiation. We still have some more months of analyzing the Planck data in order to get the good results out. And then we're also doing, we have postdocs and people we're working on doing some analysis of that to see what else we can determine about the universe and how we can combine the CMB data with data of galaxy surveys and lensing and supernova surveys and so on to try and tease out more information about it. So that's one of the activities we're working on. In fact, I was meeting with one of the postdocs today, talking about, and emailing to another, talking about what projects we're going to do in that regard in the next 3 or 4 months. So that's one of the things I'm working on. We're working on creating a new generation of detectors that might be a way, if we have one more CMB mission to measure the polarization and to measure things more precisely, we're going to need many more, but we're going to have to move from the few detectors to the tens of detectors to the hundreds of detectors to thousands. We're going to have to go up to the tens of thousands or hundreds of thousands of detectors to make it work. So we're working on developing a new technology and a new way to make focal planes and higher levels. And so we have a laboratory effort, and we are also trying to spin off from that a new detector, using that same detector technology. Something could be used in the visual and infrared, so that other forms of astronomy, for the galaxy survey, other things could use them. And so that kind of activity. And I personally have been working on a project to try and look at gamma ray bursts, that is, there appear to be these situations where very quickly there is a huge production of energy, about as much energy as our sun produces its whole life, and it's put out on the time scale of 1 to 10 seconds. And so the long ones last 10 to 100, more than 2 seconds, up to 100 seconds. The short ones last less than 2 seconds. And they put out as much energy as the sun does its whole life, or the galaxy does in a year. And so those, we believe, are a result of the formation of black holes, things collapsing into black holes, and relativistic jets ejecting extremely relativistic material, and that produces high-energy gamma rays. And we're hoping that can tell us something about testing general relativity on one hand. On the other hand, we're hoping it can help us determine how the first generation of stars formed and how quickly the heavier elements got being created and so forth. And so those are the kind of projects we're doing, and I'm also doing some things that have applied research. And so those are activities that are research. We're doing a lot of education activities. This MOOC is an example. We were supposed to be running this very day, and the day before, and tomorrow, a teacher's workshop about how to teach science in high schools. And unfortunately, the terrorist acts had some of the facilities closed, but we did several of those. I've done 3 of them in the rest of the year. And there are many other activities like that, because I see education and research as intimately linked. That you're one to understand what you're doing, you're training a new generation, but you're also disseminating your research work out to a broader audience so that people understand it and support it more and can appreciate what happens next.
Yes, in my case, probably some of you won't be surprised to know that I'm working on horizons, cosmological horizons, but also the connection between cosmological horizons and black hole horizons. So we'll see that in week 6. And I'm sure you'll have fun trying to understand what's the notion of horizon for a black hole. And I'm also heavily involved in the LISA mission, gravitational wave mission, which we'll be discussing next week. So my 2 things close to my heart.
Mention the board behind us, not
yeah, probably you don't see us.
12 hours to launch, 12 days to launch.
Yeah, so okay, this is time for conclusion. I'd like to say a couple of things. First, well, congratulate you for your questions, not just the questions today, but all the questions. There are thousands of questions, and we're completely not up to it. Of course, you answer each other, that's very good. But I can tell you that quite often, late in the evening or at night, I sit and I try to answer questions, and I'm sure it's the same with Volker. I take questions one by one, and every question is interesting, which is amazing because there are so many of you and so many questions. But every question is interesting. That's absolutely surprising to us that you can ask so many interesting questions. So.
Right, and the problem is some of the questions you ask are the same questions we've been asking for a while, and we really work hard to try and know the answer. And you guys are wondering, you don't know which ones we already know the answer to and which ones we're striving to find out the answers to.
Yeah, so that's indeed some.
So we're just like you, we want to know. Right?
And sometimes the simplest questions are the most difficult to answer. So that's because those are the ones that, as George just said, we are asking ourselves. I would like also to thank you for all the messages of support. That was very touching, and it was very comforting, for us, because life is a little difficult these days. And so thanks a lot for numerous messages that we received. We still have 2 hangouts for the coming. There is one next Wednesday, which will be live from the old Paris Observatory, and we'll celebrate the 100th anniversary of general relativity with some guests. So that should be an exciting event. And on Monday 30th, the date has changed, and I will change that on the platform. We'll have a live hangout from Kourou, from French Guiana, where there will be in the last hours preparation for the LISA Pathfinder launch. And as we're talking, we received the news that the LISA Pathfinder satellite has just been mounted successfully to the Vega rocket, which will be launched on December 2nd. So you see we are in the last steps. And so you'll be able to live live from French Guiana, the launch of the space mission. And so on Monday 30th, we will have all the people from the projects, from industry, will tell us directly from Kourou in French Guiana, what they are doing there, and also what they've been doing for this, and also in which state of mind they are a few hours before launch. Okay.
I can tell you it's very nerve-wracking, especially since it rains there often. And the morning that Blank was being launched, it was raining, and it just cleared up for a while, and it looked like a rocket went through the rain clouds, and it was very impressive.
Okay, so we'll have on the website we'll have everything live, that you can that will be at some wee hours in the morning for us in Europe. But some of you, it might be the middle of the day. You can watch live the launch of the LISA Pathfinder mission. Okay, well, thank you very much for now. I've been told that some of you had experienced some problem with the sound, so we'll check that. And we'll try to do better next time. That was our first hangout, so if there is some technical difficulties, sorry about that. And we hope to see all of you in now less than a week for the celebration of the 100th anniversary of general relativity. Thank you, George. And thanks to
Pierre and Marie Volker.
And Volker, yes, thank you very much.